Hello, this is the second part of a multiple dosing assignment video. I think in multiple places I messed up, but in the earlier video, but I tried to correct. I hope you understand. I do this video without any rehearsal, so that's why sometimes I stumble. But I'll try to make things better, perhaps in the future, not this year, next year. See here, this question is asking some of the information it is asking, which we have to calculate differently. It says the above calculation, if in the dosing regimen, may result in Cmax and Cmin value falling outside the therapeutic range. So you have to design a new dosage regimen based on the therapeutic range and population kinetic parameter. For dosage interval, you have to, as we have discussed, you have to select one of this interval. So here is based on the therapeutic range. You just remember, this is our therapeutic range. Okay, this is our therapeutic range. So here, please design a new using the regimen based and population kinetic parameters. So all this calculation we have done Cmax, Cmin, all this we have calculated based on the dose. But now this dose 180 milligram, and then it come to the conclusion that dosing interval and dose was not enough for achieving this therapeutic concentration. So this calculation, in this calculation for this region, we will use this two parameter is our Cmax and Cmin, and another you have to use this these two calculation as your Cmax and Cmin. First, it's asking for dosing interval. For dosing interval, you have to use this equation. There you go. Sorry. See, this is the dosing interval equation. So here you have Cmax and Cmin. In this case, your Cmax would be maximum concentration in the therapeutic range here. Your Cmax would be this one, this 4.1, and Cmin would be 1.5. So let's do the calculation using these values. So we will use this tau is equal to log, natural log Cmax infinity divided by Cmin infinity, and then K. So we know what was the K. We have to use that K. K was I think the K was 0.044, and then our Cmax would be ln Cmax is going to be 4.1 divided by, what is the Cmax is 4.1 divided by 1.5 divided by K, which is 0.044. If you do this calculation, you should get a dosing interval of 22.89 hours. That means you have to administer this drug every 22.89 hours. As I have mentioned to you, we cannot use 24, because if you administer the drug every 24 hours, the Cmin may go down below the therapeutic level. So So for this reason we have to go to the nearest dosing interval. Our nearest dosing interval is what? 12 hours. So this is your dosing interval. And target C average steady state concentration. Again, same equation we have to use for this. Cmax infinity, target C average infinity, sorry, it average, C average, and then we have to use C max minus C min, and each cases we have to use our therapeutic range, ln C max minus C min. So here my C max, our C max is I think 4.1 minus 1.5, and then we take ln C max 4.1 minus C min 1.5. So you should get something like 2.585 milligram per liter. So here your Cmax, let's put it here. So your Cmax, C average would be 2.585 milligram per liter. So you have your C average, then we have to calculate dosing rate. For dosing rate, we have to use that equation. Let's go back to the equation sheet. Here, I think there is an equation. Not this one. This is the equation. In this equation, I think when I was teaching, we did not discuss about this thing. So you just disregard this. You consider 1, S is equal to 1, F is equal to 1. So our equation would be, in that case would be dose divided by tau over CL. So this is going to give you dosing rate is dose divided by tau divided by CL. So here C average, if you remember this equation, if you use this equation, C average, so here we'll use this equation. C average is equal to dose divided by tau by CL. So our dosing rate is what? Our dosage interval is 24 hours. So to calculate my dosing rate, you have to just see dosing rate. To calculate dosing rate, you have to manipulate this equation like that. Dose divided by tau is equal to C average multiplied by CL. So CL multiplied by CL, it will give you C average is our C average is what? I think 22.585 times CL. So our CL was 46 milliliter, 46.4 milliliter per minute. So this will you have to do some conversion here you dose it to calculate the dosing rate. This is milliliter per minute. Here you C average is milligram per liter. So you have to convert this milliliter per minute to liter. You have to calculate this one to liter per hour, and then it should give you a dosing interval of 7.1 milligram per hour. So this would be your dosing rate. So this is going to be your dosing rate here. So here is dosing rate, dose by tau is going to be 7.198 milligram per hour. So now you have to calculate the dose. We have to use that new tau. What is that tau? I think it was 12 hour. So here you multiply dosing rate, this many milligram per hour, 7.2. Total dose is, that is dosing rate multiplied by tau, dosing interval tau. So that means you have dosing rate 7.2 times your new dosing interval is 12. It is going to be something like 72. Let's see my calculator. It's going to be 7.2 multiplied by 12 is going to give you 86.38. So this is how you calculate dose in milligrams. So this says that this is round, please round to two significant digit. You can just put it 86. The dose is 86. So let's put those values here to make things clean. Our dosing interval tau is 12 hour, and target C average concentration is going to be 2.58, and then our dosing rate which is dose by tau, I think it is 7.2, and dose would be 7.2 times 12 is 86 milligram. So now you have to calculate loading dose to raise steady state immediately. So to calculate loading dose, so we have to calculate new accumulation factor. Okay, nothing has changed, only one thing has changed, which is tau. So to calculate, we have to calculate new accumulation factor. So we have to put, let's see, RSCC is equal to 1 K tau. So our new tau is what? 12. So new tau is 12. So 1 negative K 0.044 times 12. This should give you new RSCC. New RSCC is going to be 2.44. Once you know that new RSCC, you have to calculate the loading dose. So loading dose is, this is the maintenance dose, so loading dose is DL is equal to DM times RSCC. Your RSCC is 2.44. RSCC. That means here you have to put DM is 86 and your RSCC is 2.44. So 86 times 2.44, it is going to give you 209.84, which you could convert it to 210. You need your dosing, loading dose would be 210 milligram. So these are a major thing you have to remember here in this set of calculation. For example, you have to use your Cmax. Cmean would be the therapeutic range, and this is the therapeutic range. Okay, so otherwise everything will come wrong. And when you calculate loading dose, you need to calculate RSCC. For RSCC you use the K, same K does not change, but tau you have to use new tau, which is 12 hour in this case. So always do not get confused with that which data you need to use and which data you cannot use in this set of problem. So now final one, 2 weeks after administration of the dosing regimen, which is you figured that what are the dosing regimen. We have 12 hour, dosing interval was 12 hour. Here target average concentration was steady state, target average C average I think was 7 point, C average was 7.2 milligram per liter. Dosing rate was C average and dosing sorry, this was C average. C average was what? Anyway, and dose was 86.38 milligram, and your dosing rate was 7.1 milligram per hour, 7 point, and C average was 2.585 milligram per liter. And loading dose, so loading dose you have to use a new RSCC, and new RSCC you calculate, use the same K but new tau. Now we will move to another problem. So 2 weeks after administration of the dosage regimen designed in section 2, 2 plasma samples are taken. You take from the patient, you take 2 plasma samples, and the concentration of the drug was 0.5 hour after the dose, and after the dose 0.5 hour after the dose is this, and 12 hour after the same dose was this. So we have now 2 time concentration and time point. So this thing we have to just you consider is C1, C2. Here one of the concentration is 0.226 milligram per liter at 0.5 hour, and then we have 0.864 milligram per liter at 12 hour. So in this case we have to use a different equation. If we go back, let's see the equation sheet. Here it is not different equation. We have to use this equation. Concentration, because it is time dependent, to calculate. Here we have to use this equation. Patient elimination rate constant. We do not have any other information except these two information. We have two: concentration and time point. So for this you use this equation. K is equal to ln C1 by C2 divided by T2 minus T1. So you have to use our C1. If you think our C1 was C1 is 2.26 divided by C2 is 0.864. T2 is 12 minus 0.5. So this will give you a K of, I think, 0.0836 per hour. So we have a new K. So first we have to calculate K. Our K is, this K is 0.083, or you can put 84 per hour. So now the true Cmax at steady state. True Cmax means based on this data you have to calculate my true Cmax. To calculate true Cmax, you should go back to my note so that review multiple dosing. You see here, multiple dosing here. This is the equation we are using. So to calculate Cmax, if you use Cmax and you have the C2, Ct is there at certain concentration, and we have to use e to the k tau. So what we are going to do, this multiple dosing, Cmax Ct e to the negative k tau. Cmax is equal to Ct e to the e to the negative k t. So as if you go back to this preview question, you will see that whatever time point you use, it will give you the same, it is going to give you the same result. So you just choose one of the time point, so for example, if you give C, if you take C max, so assume that you are using point Ct concentration 2.26 concentration, and then E negative K is 0.084 multiplied by T was 0.5. So this should give you a Cmax of 2.356. As I have said, you could have used the different other concentration. For example, instead of using this, if you use 0.864 divided by e to the negative k is 0.084 times T is 12. It should give you the same same result. So if it should give you same result. If it doesn't give you, just let me know. 2.356 to be your Cmax of that patient. So once you know the Cmax, you can calculate Cmin. So Cmin would be Cmax. Again, if you go back to that problems, here how we have calculated Cmax e to the negative k tau. So here Cmax e to the negative k tau. So in this case we have our Cmax. What was our Cmax? Cmax was 2.35 times e to the negative, our k was 0.084 times 12. So this should give you a Cmax Cmin of 0.864 milligram per liter. So now it is asking for volume distribution, patient specific volume distribution. What are the Cmax Cmin in this case? Our Cmax, what I found is Cmax was 2.356. Our Cmin was 0.864. And for volume distribution, we have an equation. Let's go back to that equation in multiple dosing. Here, this is the equation we have to use for when you want to calculate Cmax volume distribution from Cmax and Cmin. So here use V is equal to dose divided by Cmax minus Cmin. I think our dose was here 86, I guess. Yes. So you use dose 86, and then your Cmax was 2.35 divided by minus 0.864. This should give you a volume distribution, which is, I think in this case, 57 liter. So and then now it is asking for patient specific clearance. To calculate patient specific clearance, we have patient specific K. We have patient specific K, which is I think we have patient specific K, which is K was 0.0836. So, and we also know new volume distribution. Let's see. Our patient specific K is equal to 0.083. Our new volume distribution is V is equal to 57.622. So 60. So from this you can calculate clearance. Clearance would be V is 57.622 times 0.083. It should give you a clearance of 4.81 liter per hour, equal to 80.298 milliliter per minute. So this is all the problems of multiple dosing. So overall, so multiple dosing, you have to do a lot of things. You have to calculate patient specific data, you have to calculate population specific calculation, and also you have to do some calculation for dosing regimen. So if you go back to first, these are you calculate Cmax Cmin based on the population parameters, and these sets of equation where you calculate dosing regimen, you find out dosing interval, target dose, you find out loading dose, and then you have to also calculate some patient specific information. And then finally, please write a paragraph to briefly discuss the difference in the concentration, if any, between those estimated and in part 2 and measured in part 3, why they are different. So a number of things you can first you should make a table that for population and patient specific. So and then you can discuss that the patient has higher volume distribution. For in this case, if you think about this VL, this is patient specific, and so this patient has a volume distribution which is smaller than population. So here VL is smaller than population, and then Cmax and the dose was what is 200 in case of dose was 86 for the patient, and you see there is a difference also. Loading dose was 280, but I think loading dose were 280. We calculated using the patient specific. For this patient it is 210. So this you can do some calculation, but I'll discuss more this in multiple dosing, or Dr. Al Ahmad will discuss. I will not be in class on Thursday, so but I'll see you on Tuesday. Thank you.